Hi everyone, I am here with one Accenture coding problem that was given on 8th October 2023 during the campus placement drive. The problem is checking whether the given number is perfect or not. So what is a perfect number? Perfect number here is defined as sum of its proper divisors, that is sum of its positive divisors except the number itself. That means the number should not be considered, so all the divisors below that number, okay, they are to be summed, and if that sum is equal to the given number, then that number can be called as perfect number. Write a function to check whether the given number is perfect or not. Okay, so that is the question given. Check whether the given number is perfect or not. Input. Two sample inputs are given here. 22. 22 is not a perfect number. So that's why the output is to be given as 0. So why this 22 is not a perfect number? So the divisors of 22 are 1, 2 and 11. As they have said that the number itself should not be considered, we should not consider 22. Okay, so the divisors are 1, 2 and 11. Their sum is 14. So it is not equal to 22. So that's why the number 22 is not a perfect number. So the output for that is 0. Okay. Then another input 6. The divisors of 6 are 1, 2, 3, and of course 6 should not be considered. What is the sum of these divisors? 1 plus 2 plus 3, that is equal to 6. That's why the output is produced as 1. Okay, so the constraints are not available here. I assume that for number based problems they can easily go up to, as they have said the divisors are positive, the constraints may be like this: 1 less than or equal to n less than or equal to, they can go even up to 10 power 9. The most common I mean this upper bound for number based problems could be like 10 power 5 to 10 power 9, and this is my expectation. So I am not able to fetch that constraint details from this question, from the available question. So I am assuming that it could be at minimum 10 power 5 and at maximum it can go to 10 power 9. Okay, so this may be the constraint associated with this problem. Okay, now let us work towards the solution. I have written Python solution for this one. First I have attempted this problem by direct method. Direct method, we can label it like brute force approach, naive approach, etc. I am calling it like direct method. So I am writing one function. Def is perfect. It is taking one parameter num. It takes one parameter num. Sum is initially set to 0. Then for I in range 1 comma num divided by 2. So some people, they will consider it like up to num. Up to num. So it is unnecessary. Why? Because for example, if you take 6, what is the highest number other than 6 that will divide 6? 3. That means it stops at 6 by 2. So that's why I am considering num divided by 2 plus 1. So this is just common sense. We need not run the loop up to num. So thereby we are reducing half of the number of iterations. We are bringing down the number of iterations from num to num by 2 with this approach. Even though it is a direct approach, as it is just common sense kind of thing, I am directly applying it. Okay. Now, if num is divisible by I, add that I to sum. Finally, after this for loop, check whether sum is equal to num or not. If it is equal, if they are equal, return 1, otherwise return 0. Then in driver code, we will read the input and call the function. The input is read into n. Then we are calling the function and simultaneously we are printing the return value of that function. That will be either 1 or 0 depending on the number. This is the code. So though I am reducing this number of iterations to half, still the time complexity can be said like big O of n. Even reducing it to half will be a bigger number. Let us assume the input given is 10 power 5. 10 power 5 in the sense 1 lakh. Even if you reduce it to half, the number of iterations will be 50,000. Though it is the reduction of number of iterations, still it is not efficient. We can improve it further. For this improvement or for this optimization, what is the approach I am going to use? I am going to use the logic that we apply for checking whether the given number is prime or not, using square root method. Prime or not, using this logic I am going to use here. Okay, so this will bring down the time complexity from big O of n to big O of square root of n. Let us assume n is 10,000. The square root of 10,000 is 100. Even though in our direct approach, even if you reduce the number of iterations, this will still remain at 5,000 number of iterations for n equal to 10,000. And our square root method, efficient method, will stop at 100 iterations. Now you please tell me which is best here, this approach. So if n is a bigger value, you must apply this square root method. Okay, so one or two test cases may be designed to check this time complexity. Okay, so if you do not take care of such optimization when n is big, for example, n is given in the range 10 power 5 to 10 power 9. For number based problems, this is quite common. Then you must be careful about this optimizing the problem. And if you optimize, if someone looks at your solution, they will get impressed. So there are high chances that your code may be appreciated or you may be selected for final rounds. Okay. Let us go through that efficient approach. So as I said, I am going to apply this square root method. Sorry. I am writing the function is perfect num. Here I am assuming sum to 1. The reason for this is, if sum is assumed as 0, when I start with I equal to 2, this 1 may be missed. So that's why I am assuming sum equal to 1. As I said earlier, I am going to apply the same logic that I apply for finding whether the given number is prime or not using square root method. The same logic I am going to apply here. Okay, I equal to 2. I starts at 2 while I square less than or equal to num. This is same as, instead of writing I less than or equal to sqrt of num, I am writing it indirectly I square less than or equal to num. Why I am writing it like this is, square root is a float value. I have to explicitly convert it to integer, and then some plus 1 needs to be added, and moreover I have to import math package to work with this square root. So to avoid all that additional efforts, I am simply putting it like I square less than or equal to num. These two are very same. Okay, now if num is divided by I exactly, sum equal to sum plus I. Okay, very good. What is this one additional step here? Sum equal to sum plus num divided by I. Why we are considering this like this? Suppose if num equal to 6. What is square root of 6? What is square root of 6? It is 2 point something. That means the iterations will stop at I equal to 2. But we know that 3 is also a factor of 6. How to include that 3 into account? How to consider that 3 into account? Then I will be getting 6 divided by 2. 6 divided by 2 is 3. That's all. So this step is to catch these additional factors. Okay, why? Because we are stopping so early and one factor may be missed. Okay, so for that reason we are considering this additional step. Then remaining logic is very same as prime number. I plus equal to 1. If sum equal to num, return 1, else return 0. Then in driver code we read the input and we will print the result of this function. That's all. I hope you understood this. Let me run this code and let us give different inputs. So first, perfect number or not, using direct method. Let me run this code. What is the time complexity of this direct method? Big O of n. Okay, so let me give 22. 22 is not a perfect number. This is one sample test case. What is the expected output? 0. Yes, our code is printing that. Let me give another sample input, that is 6. We must get 1. Yes, our code is getting it. But what is the problem with this direct method? The time complexity is, though you are reducing it to half, still the time complexity is said to be big O of n, where n is the number. Okay, not input size here, number. Next, efficient method. The time complexity of this efficient method is, the number of iterations will go up to big O of square root of n. What is n here? It is not input size, it is number here. Okay, then let us go through the function as I have explained earlier. This is same as I less than or equal to square root of num. Okay, remaining all I have explained earlier. Let me run this one. Let us just check whether it works for sample test cases or not. 22. 0. Let me run this again. 6. 1. Yeah, it is working perfect. So please be mindful about the time complexities when n is large. Okay, so you must be careful about this one. Suppose if n is given as 10 power 9, deliberately 1 or 2 test cases might be designed to check the optimization of your code. Please be careful about it. Okay, so those who are preparing for Accenture placement drive are those who are practicing Accenture coding questions for offline or off-campus drive or on-campus drive. Please go through the playlist in my channel Accenture. Then please practice pseudocodes also. I have put 15 pseudocodes so far, that is under pseudocodes playlist. Please go through them and practice them also. They are very much suitable for Accenture. And if you have liked the logic I have presented here, hit like button, subscribe, share it with your friends. Very importantly, please share your opinion in comment section. Okay, thank you.